Welcome to Hot Chips 28. Session 6, Emerging Embedded.
All right. Welcome to the Emerging Embedded session. My name is Michael Taylor. I'm a professor at UC San Diego. Our first talk is entitled A Zero-displacement Active Ultrasonic Force Sensor for Mobile Applications. The speaker is Sam Sheng. He's currently CEO and co-founder of Sentons. He's an ex-digital guy turned RF guy turned touch sensor guy. He did 3 degrees at Berkeley in electrical engineering, terminating his PhD. At that point, he ran out of degrees, I guess, and decided to go into digital and then RF and then sensors. Without further ado, here is Sam.
So, good morning. So my talk today is actually about zero-displacement active ultrasonic force sensors, which is quite a mouthful. So what are we actually talking about here? So this is actually where this was all born. So if you ask an RF engineer to build a touch sensor, this is what you get. I mean, fundamentally, think about the entire kind of art or practice of touch sensing. You're really trying to determine place, basically X, Y. You're trying to determine basically where something is. So if you're an RF guy, the first thing you think about is, fine, we're going to use scattering or absorption of a propagating wave. All right, we call it radar, sonar, that's what an RF guy would call it. Fine, we'll use that to try and track where your fingers are. So you want to measure the scattering absorption of a propagating wave. Guess what? The radio guys have been doing it for the last 20 years or 40 years. We call it equalization. Okay? The last thing where things get interesting is you need sub-millimeter accuracy. So these days with your iPhone, you're expecting your finger to track to better than a millimeter in terms of precision. The challenge with RF is that to get to a millimeter wave, you need about 60 to 100 gigahertz in terms of carrier. So that's where things get dicey. All right, it's really, really tough to build a 60 to 100 gigahertz bit of electronics, especially for consumer electronics. So where we got started was we said, fine, can we eliminate the 100 gigahertz requirement by eliminating the speed of light? Okay. The reason why we need to go to these frequencies is because the speed of light is too fast. So instead of using EM, can you use ultrasound? Okay. So you literally lob 5 zeros off the speed of the wave. Guess what? Instead of needing 100 gigahertz, about a megahertz is more than sufficient. So, which brings you to the concept of ultrasonic propagation in plate solids. Okay, so the way the touch sensor is built, we literally vibrate the surface of the glass. So we are moving any surface that we touch enable is vibrating. Okay, and it turns out that there are many, many different possible propagation modes actually for ultrasound in plate solids. All right, and if you thought Maxwell's equations was bad, believe me, this is actually, turns out, it's a 4th order partial. I won't go into the math, but just suffice it to say that if you look at sort of 2 possible modes, right, the glass bending this way, just call it A0, or versus a wave snaking along in the glass, call it S0, those are 2 very, very different possible propagation modes. The interesting thing is they propagate at different speeds. One of the big assumptions that we make in the world of radio is that the speed of light is the speed of light. It turns out that the speed of sound is very much not the speed of sound. It's very highly dependent on what frequency you're at and which mode you're talking about. Okay? So one of the things that immediately break is that concepts of linear equalization, things like that, don't quite work. One of the most dramatic things is that we always assume that a radio wave striking an object bounces off, it leaves at the same angle it came in at. Not for sound. So Snell's law is generally not applicable. So you have to really start to monkey a lot with the propagation equations and how you view equalization. The net of it is that if you sort of squint sideways, you can actually make what we call a linear equalizer work. Okay? So, fine. So the propagation of a sound wave through glass, take my word for it, actually can be made to work. What's the equivalent of an antenna? Okay, so we think about a piece of metal, whatever, inverted F. Fine, we have antennas for radio waves. What's the antenna for a sound wave? The antenna for a sound wave is, amazingly enough, a very cheap device called a piezoelectric ceramic. All right, this is absolutely the sound wave equivalent of an antenna. It takes electric field and converts it into mechanical motion. All right, it looks like a parallel plate capacitor. Electrically, that's its electrical equivalent model on the right. Okay, and it induces strain in the glass directly proportional to the applied voltage. Okay, and it's exceedingly common. Actually, the simplest form of piezoelectric ceramic that you'll find is your quartz crystal. Your crystal oscillator, billions of these things are made. They're all based on sound. Okay, the resonant frequency of a quartz crystal oscillator is set by a sound wave propagating between the two terminals on your crystal. Okay, so trust me that this is exceedingly cheap. It turns out that this is literally what I would call a miracle material. It's literally, you make them the same way as you would make a ceramic capacitor. You just pull them, and you can get a tremendous amount of mechanical transduction as a function of voltage. Okay, so in some sense, we've solved sort of the two big problems, right? How do you interface the sensor to a piece of glass, and how do you propagate the wave through a piece of glass? Okay, so how do you turn that into a touch sensor? Okay, so this is our basic sensor technology. So we use what we do is outside of the visible field. So in the border of the glass, we actually literally glue piezoelectric ceramics to the backside of the glass. Okay, so they're on the back, nothing on the front, no bezel. It looks just like a capacitive touch sensor inside your iPhone. So all the components are sealed, and then the piezoelectrics on the backside will vibrate the entire surface of the glass. All right, so on the previous 2 slides ago, when I talked about the A0 propagation mode, that's what you're going to find. That's where your finger will interact, because the whole glass will be moving up and down. As you contact the surface of the glass, you're going to disrupt that wave. And it's no different than a human being walking into a room with 802.11. Every radio in the room equalizes. Okay? And so what we've done is we've taken all of that equalization technology that has been developed for radios and have used it to effectively compute the maximum likelihood positions of fingers on glass. That's really what we've done. As I said earlier, instead of needing 60 gigahertz, 500 kilohertz is more than sufficient. Okay? And I can build a lot of interesting technology at 500 kilohertz. Okay? The other interesting property is that if the surface can conduct a vibration, okay, I can turn it into a touch sensor. It doesn't have to be glass. All right. Metal, in particular, has proven to be quite interesting of late, and I'll give you a demonstration a little bit later about sort of how we use touch sensing on metal. But the net of it is that we can turn metal, plastic, glass, pretty much anything into a touch sensor. Okay, so this is actually not a simulation, assuming my video plays in the next slide. So this is actually a laser vibrometer actually measuring the propagation of a wave launched from a piezo and a finger contacting the surface of the glass. The thing to note, the amplitude of the glass deformation here is about 20 nanometers. Okay, as I said, this piezo ceramics are a miracle material. It's amazing how sensitive they are to vibration. And so this is the wave launching from the piezo in the lower right corner. And normally this plays at 30 frames a second. It's not streaming, actually. It's doing something. I'm sitting here. It's having some problems. Anyhow, there's actually a touch about halfway up, about in the middle of the screen, there's actually a touch point. If the video actually finishes playing, you would actually see that when the wave strikes the finger, it actually puts out ripples. All right, and mechanically, it looks actually no different than ripples on the surface of a pond. Okay. So, touch, and on the title of my slide was actually all about force. Okay, so what about touch and force? All right, so we have 3 variables, x and y, which is the touch position, and then z, which is force. All right, so if you look on the right, those are actually the measured waveforms actually at each piezo. All right, so what we have is we have an array of transmitters. We have an array of transmitters and receivers mounted onto the touch surface. Transmitter launches a pulse in the glass. The receiver sees that, okay, a finger has come down. I have another set of pulses that have shown up. So here are the questions that you have to answer using a piece of silicon. Which pulse goes with which finger? All right. Edge reflections off the sides of the glass can cause multiple pulses from a single touch. You need to go equalize those out. In general, because of the speed of sound, the fact that the speed of sound is so slow, the time of flight between so from a wave traveling from the transmitter to your finger to a receiver, the time of flight there actually tells me position. I can triangulate based on time of flight. Now, here's the interesting one. So I can solve xy based on time of flight. The z variable, which is force, comes about because the amplitude of the scattered pulse is proportional to how hard you're pushing. Okay. And so a bit of intuition. Wave is traveling like this, your finger is at this point. If you're pushing lightly, the amount of energy that you're going to scatter is actually relatively small. Okay. Versus the other extreme, when you're pushing quite hard, the glass can't move. All of that energy's got to go someplace. And so what you find is that the amplitude of response is linearly proportional to force between about, say, 20 grams all the way up to, we haven't even measured the upper limit, call it 10 kilograms. But the one interesting thing about this particular touch sensor, in addition to the fact that it works on metal and doesn't require any lamination and it's easy to manufacture, is that we simultaneously measure all three variables. We simultaneously have to measure x, y, and z and solve for all three simultaneously. So a comparison to existing sensors. Okay. The upper row is what you would find in your iPhone. Okay. This is what a projected capacitive sensor looks like. It's a piece of glass, and you laminate indium tin oxide, another dielectric, more indium tin oxide. Yes, there are many different constructions, but fundamentally, it's a manufacturing problem. Okay, a capacitive touch sensor literally consists of a lot of work in the manufacturing side to create this array of sensors underneath the surface of the glass. As a result, yes, there is complexity in the silicon, but relatively speaking, the algorithm that needs to sense is Node 1, have you seen a change in capacitance? Yes, no. Node 2, have you seen a change in capacitance? Yes, no. So algorithmically, you don't have a whole lot of complexity. So philosophically, the way we approached the problem was, okay, what's the simplest sensor you possibly can build that can get you to multi-touch? Take a piece of glass, glue a bunch of cheap piezo ceramics to the backside, outside of the visible field. So your yield is fantastic. There's nothing that the user would ever see. Okay, there's nothing laminated in the visible field. And that's it. That's the entire assembly process actually for our sensor. Okay. Now you've got a silicon problem on your hands, because now you have to take the waveforms from every one of those receivers, generate the transmit waveforms, figure out all the receive patterns, and figure out where the touch was located. Okay. And so we've actually reversed the problem. We've converted the problem from a manufacturing issue to a silicon problem. Okay. And we're still on the good side of Moore's law, actually. Every generation, every node actually helps us an awful lot in terms of both power and size. So let's talk about two specific technology use cases. And we've had a lot of interest actually in this technology actually for both of these. So cover glass force sensing. So image courtesy of our friends in Cupertino. So the iPhone 6S. All right. So they incorporated a force sensor actually into the iPhone. Okay. And so they actually can sense both X, Y, and Z. Okay. XY is your traditional capacitive touch sensor, and to sense Z, they actually incorporated another layer. Okay, so that spongy layer sits behind the LCD and depends on physical deformation of the glass. When you push on your iPhone, you are actually bending the glass in the LCD to the point that two parallel plates actually are compressing, and that's how they sense. Now you think about how thin your phone is, you have to ask, well, okay, how thick is that layer? About 0.2 of a millimeter, give or take. Manufacturing tolerance, it's a tough thing to build. Okay. So the our zero displacement force sensor, okay, it provides actually a pretty big advantage actually over this. It does not require deflection of the glass. And the way to think about it is the difference between a DC response and an AC response. All right, so instead of requiring the user to provide a DC, I physically am moving the glass, we effectively pre-bias the glass with an AC waveform. We're actually moving the glass along using our transducer, and we're looking actually at how the force of your finger actually interacts with that wave. So we actually do not need this complex array of capacitors behind the glass or physical deflection of the glass itself to sense force. Okay? Another way of thinking about it is we're sensing force by proxy. Okay? We're sensing force by looking at the interaction of the contact object with the wave. All right? So we can detect force on basically highly rigidized surfaces, and the demo in a couple of minutes will actually demonstrate that. So you ask, okay, fine, if I were to, say, install the sensor into the front of a phone, this is actually the measured force heat map actually with our sensor installed actually in the front face of a phone. So you can actually see there are hot spots, because as you push on the glass, it still will bend, and if there are certain structures in the backside that start pushing on the back, that's where you get the hot spots, okay? And so we actually work with the customer's touch sensor to normalize out all of this. This is highly repeatable actually basically from phone to phone. So we often get asked, okay, so fine, is your touch response or your force measurement actually a function of contact area? So each one of those lines is, again, we're measuring force by proxy. So each one of those lines is the reported force response for a four-exchanging contact area. So we actually have 3 different probes that we're pushing down with what should be a straight line. If we normalized out all 3 area contacts, we should get sort of a line, 3 lines on top of each other. But this gives you an idea of the sort of the aerial contact sensitivity actually of the sensor actually in terms of its force measurement. Okay, and so the purple line is kind of nominal. A 1 kilogram force gives you approximately a 1 kilogram measured response. The green line, which is smaller slightly, is a 7 millimeter probe tip, and the blue line is a 12.5 millimeter probe tip. So there's a weak dependency actually on contact area. Most of what you're measuring is actually true force. Okay. So sensor integration. So people ask how we actually install these things into a phone. It turns out that on the north and south edges of your phone are just about the only place in your phone left that actually has some volumetric space available to actually install a sensor. So we actually install sensor strips by mounting piezos onto flex, and we literally just glue the entire assembly on the north and south edges of the phone. Again, we do not require lamination actually in the visible area of the phone. So we just mount them just behind the phone, or just behind the glass, actually above and below the LCD, and that's actually where we measure, how we measure force. So that's cover glass. How about touch and force enabling the rest of the phone? Okay, so let me switch over to a demo. As I power this up. What we've done is we've actually applied our sensor to, how about the edges? Okay, the 2 sides of the phone. Okay, so in particular, we mount piezoelectrics along these 2 edges. Okay? Now, keep in mind, this is an aluminum case. No capacitive sensor could ever function through a metal case, just because the metal is going to short out the electric field of the capacitor. We can simultaneously sense touch and grip force. So I can tell you what hand you're holding it in and how many fingers are contacting the edges of your phone by just using our ultrasound by propagating waves along each edge of the phone. And, assuming that the technology gods are with me, what do you know? It worked. So what's unique about this cell phone, and you can come up after and take a look, the cell phone actually has no switches, cutouts on the edges of the phone. The edges on this phone are perfectly smooth. So you can see how hard I'm gripping is determined by color, and it's tracking basically every finger position actually on the phone. Now, again, about the whole concept of zero displacement, you think about the sort of the rigidity of this metal structure. I'm not bending this phone. This metal is not, as I lightly grip this metal is not bending in any perceivable way, shape, or form. What we've got is we have ultrasound waves propagating along the surface of the metal here, and we are tracking basically based on how much energy is scattered and absorbed of that wave. So there's been a lot of interest actually around sort of touch enabling the rest of the case of the phone. And from a practical standpoint, our phones are trying to become kind of everything. So taking advantage of the real estate, the metal case on the back side, sort of touch enabling the back, the edges. You can imagine one use case is you want to take a selfie, just squeeze. Don't go hunting for the button anymore, right? Actually, I'll tell you, in all of our user experience testing, it turns out that the squeeze to shoot the selfie is the #1 popular use case. So it's amazing how much technology gets built to solve that problem. Yeah, I've had some really interesting marketing conversations. All right, so on to the more interesting stuff. So for those of us who build chips, so this is the ASIC architecture. Okay, so we actually have 8 fully custom receive paths to interface to the piezos. We have fully integrated transmit drivers. Okay, so we are driving these piezos actually at 2.8 volts. Okay, which gives you an idea of, a lot of times when people do piezo work, they're like, 100-volt drive. This is fully integrated. This is a standard CMOS process that we're fabbing the chip in. So we're actually driving our piezos at 2.8 volts, which says that it's a good thing we're a bunch of RF guys because we're not afraid of like microvolt level signals on the receiver. Okay, so that's actually so we have a full custom analog front end. And then there's for the kind of correlation, decorrelation sections, there's a digital that's fully synthesized. Okay, so we have custom digital actually for this portion. And then we have a 16-way parallel DSP engine that we actually licensed from Tensilica that we're using actually for the back end. And then there's a small supervisory interface to the host. Okay, this is actually 5-volt capable. Actually, if we actually do want high voltage drive, for most of our customers, actually in the cell phone space, this is actually 2.8. We have 13-bit. We actually truly get 13 bits actually out of 8 calibrated SAR ADCs actually on the analog paths, and then actually the overall receive dynamic range is slightly north of about 60 dB. It's actually almost 70. Okay. To give you a perspective, actually about in some sense how good the tools have gotten. Okay, the entire engineering team that built this from scratch, assuming you count me actually in the engineering team, was 8 people. So we fully integrated all of the digital, did the custom digital, and all the custom analog with 8 designers. Okay, so I think that's more of a testament to the tools more so than anything else, which is actually kind of a frightening statement. So dye photo, so it's about 20 square millimeters in a TSMC 65 nanometer standard CMOS process. 5x5 CSP, max CSP clock is 200. Our big touch sensor one actually clocks closer to 500 megahertz, but for power reasons, actually the mobile ASIC actually clocks at 200. Very, very standard I/O voltages. This gives you an idea of the power consumption. So scan to wake, where you are squeezing the phone to wake the phone up. Little under 1 milliwatt actually at a 5 hertz report rate. And then max scan rate, actually 100 hertz, you're playing a video game, we actually draw about 14 milliwatts. Okay, so just to conclude, it's actually a very different way of building a touch sensor. So it actually allows for a wide variety of touch and force sensing. I mean, one of the big advantages we have is that fundamentally we get X, Y, and Z actually effectively for free actually with the sensor. We can sense force without requiring surface deflection, which allows you to integrate a force sensor into places that you otherwise wouldn't be able to. And people are just having a lot of fun right now with us actually in terms of industrial design. What could you do with being able to touch enable the edges of a phone? So thank you very much.
Okay, questions for Sam. Let's start over on this side.
Yeah, Nathan Brookwood, Insight 64. Very cool. I'm impressed. With the piezos, do you have to have different piezos for inducing the vibration and sensing it, or are they full duplex?
Architecturally, you can do it either way. You actually have to introduce either some form of echo cancellation or diplexing if you're going to do simultaneous function. The SNR loss is about 15 to 16 dB if you try to actually do an echo cancel diplex type arrangement. So at least for this iteration, right now the TXs and the RXs are distinct.
They are distinct.
They're distinct right now. Although at some point along the line, we may finally actually go back to the diplex structure.
Hi. This way?
Oh, sorry.
Okay. Koji Suginuma with Eizo newspaper. So 2 quick questions. So what is the difference between the conventional ultrasound touch sensor and yours? And second question is the resolution of the, how do you say, the positioning.
Yeah, so position resolution actually in, for example, Windows 8 testing, where if you're familiar with that, our typical resolution is better than 1 millimeter, typically about 0.8, 0.8 with a sigma of about 0.1. The other ultrasonic touch sensors, ELO probably being the company that has produced most of those, so they actually use SAW. So that's the dominant ultrasonic, quote, touch technology is using a surface acoustic wave. The challenge with that is that it's a surface acoustic wave. And so what you find is that the transducers actually need to be on the same surface as the touch. Okay, so if you look at like in, I don't know, like a supermarket where you see an ELO touch sensor, they usually have a pretty big bezel to cover the circuit, the ultrasonic transducers. The other big difference is that they attempt to create kind of ultrasonic pulses in columns and rows. So we actually try to uniformly vibrate the glass. So, I mean, I didn't go into the whole issue of shadowing, but one of the big problems actually with existing ultrasound solutions is the issue of shadowing. Because what happens is they fire a single pulse, and then they use an ultrasonic diffraction grating to create columns and rows of pulses, and they literally see where a pulse is missing in the receiver. Okay. We, on the other hand, try to uniformly vibrate the surface to avoid shadowing. The point that you start creating columns and rows, you can't distinguish, so you can tell this, you can tell this, you cannot tell four contact points. So that's actually what we're trying to do. So we actually uniformly vibrate the surface.
Excellent idea. Thanks so much.
Okay, over on the right.
Cavium. So if you uniformly distribute and calculate everything, how do you deal with multi-touch?
So the amount of energy absorbed or scattered by your finger is only about 3%. Okay, so what happens is, let's just say I have a grid of contact points like this. Okay, what happens is actually the ultrasound wave actually keeps going. So actually the amount of energy that you get from a touch-to-touch scatter is incredibly small. So we actually don't see, for all intents and purposes, you can assume that all the fingers are actually linearly independent of each other.
Good, thanks.
Okay, Kevin Krewell from Interiors Research. You talked about glass and aluminum casing. What about polycarbonates and other plastics? Are they rigid enough?
Yeah, actually, so the Young's modulus of polycarb or PET, PMMA is about sort of a factor of 10 lower than glass and metal. So on relatively small plastic surfaces, let's just say less than 12 inches, it's not an issue. Once you start getting above 12 inches, the amount of propagation loss you get actually from absorption in the glass or plastic due to heating starts becoming untenable. So we'd have to go to much higher drive voltages if we were going to operate on, let's just say, a very large piece of plastic. But certainly something the size of a cell phone is a non-issue. So we've got multiple customers actually working on polycarb.
Okay, cool.
Hello, Satoshi Matsushita, NEC. A lot of people are using a glass protector or something, or sometimes the scratches, some scratches occur. Is there any effect by that?
Yeah, so if you, let's just say, I mean, you dent the side of your, let's just say you dent the side of your phone, right? You dropped it, or your son decided that he wanted to use it for a discus. Which has happened to me. So what happens is that we have a continuous background calibration. So you can think of it as we have to measure what the baseline response is continuously. Actually, the more dramatic case is not even scratches. So if you dent the side of the phone, it gets equalized out pretty rapidly. Just the baseline just gets renormalized. The more interesting thing is what happens when you go from a, let's just say, freezing cold outside to a warm room. That's the more interesting question, because the temperature transient and the TempCo actually on piezo is actually quite high. So again, we have to continuously track all of that. We have no choice. So,
last question.
Hello. My name is Matthias from Hawaii. I found a question, does it work underwater?
Interestingly, yes. Yeah, actually we have, there's some really interesting use cases for underwater sensing. In particular, underwater operation of your phone actually is a rather interesting use case. So.
Thank you.
Okay, on that note, let's thank the speaker.
Thank you.
Okay, our next talk is entitled Quantum Dot-Based Imagers for Multispectral Cameras and Sensors. Our speaker is Dr. Emanuele Mandelli, who is VP of Engineering at Invisage Technologies, which is based in Menlo Park, California, and focuses on advanced materials and camera platforms. He has over 20 years of experience with image sensors, X-ray, and particle physics detectors. He started his career at Lawrence Berkeley National Labs. He holds a PhD, MS, and BS in electrical engineering from the University of Pavia, Italy.
All right, thank you. All right, I'm going to talk about quantum dot-based image sensors and cameras for multispectral applications. This might be a little new to this audience, so I'll try to keep it simple. This is the what I'm going to cover, introduction, how we make quantum film, how does a sensor with quantum film on it looks like and works, and the advantages and the problems we are trying to solve. So everybody nowadays have digital cameras in their pockets, in their phones, and they work great, but still there are some problems. For instance, if you try to take a picture in this room, it's not going to be a great picture. Problems are if you have a very bright object in the background or as your subject, everything else dims down and you're going to lose details in that areas. So that's the first problem, backlit shadows. You need a lot more dynamic range that you might think. The second one, moving objects or moving cameras are not producing great pictures. And that's due to the architectural choices that work nowadays in compact cameras, which is the readout is done row by row, and so is the exposure. So you expose an image on a row by row basis, so that every row gets a little bit of a different timestamp. And that's what happens when you vibrate a camera. You get an image that looks like a jello. Third problem, if you're in a dark room, the pictures that come out are very noisy. And interesting enough, 90% of the pictures that people take with their cell phones are in very dim light conditions, like bars, restaurants, and so on. So those three are very important scenes that everybody experiences every day. Why this is problematic is the root cause is that image sensors nowadays use silicon, and silicon is not very good at absorbing light. That goes for visible spectrum. Right now, there are a lot of applications that require infrared light, and the advances we made in image sensors in visible, like on your cell phones, are amazing. Like the pictures you can take with your cell phones are really great, but if you go into infrared now, it's a new kind of field. Silicon is even worse in infrared, and so you get low resolution because you need larger pixels. Usually, like for security cameras, night vision cameras, you're using 850 nanometers, which the eye, the human eye, can still see. And so your LEDs that you use for active illumination look like a red glow. If you look at your security cameras, you always see this round red eye that is looking at you. It's particularly problematic for baby cameras, the one you put to see if your baby is sleeping. As soon as you turn off the lights, the red ring turns on, the baby gets scared and starts crying again. So we want to get rid of it. And moreover, nowadays, there are a lot of applications where you require to get depth information. And that's one really clever way to do it is like the kinetic camera of the Xbox. It's called structured light. You basically have an illuminator with a pattern of dots, and then you look at your image, and you look if the dots are very close together, means the object is close. If they're spaced out, the object is far. And that works great. You can play video games and everything in your living room. If you take that system outdoors, it stops working. The reason is the sun is very powerful, and it's going to override your illuminator. So if you're planning to use this system in an autonomous vehicle, for instance, in a car, unless you're driving only in your living room or garage, you need something different. We think the solution could be quantum dots. This is how they look. A quantum dot is a confinement dot of 6 nanometers in diameter. We make a lot of them, and they look like a crystal structure. What we do, we make a solution in a liquid, and so you can see a vial with some quantum dot fluid. What does it do? Quantum dots, they can actually see a different wavelength, and the reason is the quantum dot size, that diameter of the dot, is also controlling the equivalent band gap. So if you look at silicon, you have a constant band gap. You can't move it, right? But in quantum dots, the technology allows you to change the size of the dots and tune them for a specific wavelength. So that's very powerful. You have a semiconductor material, and you can control the band gap. So how does this work? You put a solution of quantum dots of different sizes, and you illuminate with light, and you get these kind of spectrums. The dashed line is silicon. So silicon is actually not too bad in the visible light, which is between 450 and 650 nanometers. From blue, 550 is green, 650 is blue, is red. And then infrared starts from 650 and on, but you can see the drop of absorption is really dramatic for silicon, while for quantum dots, depending on the size you pick, and you can pick multiple sizes and mix them up, you can extend the absorption to longer wavelength. These are actually measurements. It's the same concept, wavelength versus quantum efficiency, which is a translation of absorption, is how many photons you can actually collect and convert in electrons. And you can see that around 850 nanometer, silicon is about 20%, and that's what the night cameras are today are using. You have this 850 nanometer illuminator and 850 nanometer camera. We want to push it all the way to 950 and on, and there are big advantages in doing that. Now that we understand how the quantum dots work, so they absorb light and the different wavelengths with different sizes, they convert into electrons. What do we do with that? The two cartoons are today's image sensors. They are BSI, backside illuminated. So here is where your wiring metals are. Here are your transistors. And this is the bulk of the silicon, which is used to absorb photons and convert in electrons. And then you put color filter arrays to generate RGB colors. What we do instead, we keep a front side illumination, which means we don't have to flip the wafer. It's a lot cheaper technology to do this. BSI is expensive. And all we do is we coat on top of the wafer a very thin layer of quantum dots. And we read them out by patterning this quantum film with electrodes. And the advantage is that not only you have a very easy integration process, but you're also freeing up a lot of the silicon area that in this situation you're using for your photodiodes, because you're basically stacking them on top in the quantum film. So you have more room for your transistors down here. So a lot of more either functions or smaller pixels. So this is how it looks like cross-section. You have the micro lenses, light comes in, color filters. There are some layers to buffer the quantum film and to adapt for wavelength and reflecting coating. Quantum film is this one. It's very thin compared to the, for instance, color filter. It's about half a micron. And all we do from all we need from your regular CMOS wafer is on your top metal, you have to pattern the electrodes, and those define the pixels electrically. How we do it? We use a standard silicon fab. We use TSMC, and we get the wafers from them. It's a standard logic process with all these little contacts coming up at the top level. And on top of it, we spin coat this quantum dot solution, and we then encapsulate that with buffer and anti-reflecting coating, and then we send it out to another partner to do color filters and micro lenses. So a very easy integration flow. We have our own fab in Taiwan to do this step. But this is, again, very easy spin coating process. This is how the chip looks like. This is the layout. The layout is basically a big array of pixels, and that's where your light comes in and you create the image. One ADC per column. We do single slope ADCs. They're very easy, very low power, very fast. And then there is a digital section that does the image processing. So advantages. We touched a little bit on this already. So the response of quantum dots, it's a lot higher and better than silicon. This is a wafer that comes out from TSMC. As soon as you coat it, you can see there are all these black dots are where the quantum film has been deposited and etched out. And they're dark because quantum film absorbs all the photons. Second advantage, as I touched upon, you're freeing up real estate in the silicon, so you can use that for the purposes that you need. One purpose is, for instance, full well. You can, with quantum dot sensor, collect a lot more electrons, therefore your dynamic range is going to be extended. This is what a DSLR camera looks like, large pixels, big full well. This is what a cell phone looks like, very small pixels, small full well. We are right in the middle with the same pixel size of the cell phones, but dynamic range of a DSLR. So this is what happens. If you have a picture and you take it with a current cell phone, the sky, the highlights on the face or the windows gets blown out. The equivalent image taken with a quantum film looks a lot better in terms of dynamic range. Another comparison, the golden standard for image quality is actually still Kodak film. Those old cameras with the film that you have to bring and develop outside. This is one of the best cell phone cameras we have around today, and this is with quantum film. You can see again that highlights are a lot better here. You can see details in the window, you can see details in the dark. Second problem, the rolling shutter artifact, the fact that image sensors expose one line at a time. We can overcome that because we can do a global exposure for all pixels at the same time, transfer the charge in the silicon, and then read it out row by row, which means that the snapshot you take is done at the same time for all pixels. So this is what you get with a rolling shutter camera. This is what you get with quantum film global shutter. So your shot, even if the camera is moving or the subject is moving, is very sharp and neat. Infrared. Why is infrared interesting? Well, lots of applications today. We have drones. They need to know where they're going. They need to avoid obstacles. You need cars that help you driving or self-drive. You have all these AR, VR applications coming up. They need to know where you are in the room. They need to know where other objects are in the room with a lot of resolution. And you need also applications like identification. Windows Hello coming up. All the laptops will identify your face with an infrared image, as well as your phones will unlock just looking at them by identifying your iris. So lots of applications, and they're coming up now. So we are right in the middle of it. Structured light, it's what I was talking about in the beginning. This is a description like a cartoon. You project, you have this VXL that projects like 3,000, 6,000 dots on your image, and you can tell an object that is close to you, like a ball with a pattern of dots that are very adjacent, or if they're far apart, the object is far away. This is the spectrum of the sun at sea level. You can see that at 850 nanometer is really still pretty high, while at 940 there is a water deep, so there is very little light from the sun. So going from 850 to 940 nanometers in your illuminator enables you to go outside your living room and operate outdoors. This is what we do with the quantum film. We not only have an increased sensitivity, we hit 35% quantum efficiency at 940, but we can see definitely from this comparison picture that once you illuminate with a 940 nanometer illuminator, you can see objects, you can see the dots, you can determine which one is far and which one is close, while for regular silicon image sensors, it's really hard to get any signal out of the noisy background. Again, reiterating, at 940, quantum dots can give you 35% QE, so it's a 5x over silicon. And this one is the important picture, is quantum film can give you 940 nanometers, global shutter, and small pixels all in one. You don't have to pick one or the other. If you do a comparison with current silicon, this is the problem you have. You have, you can take an image at 940 nanometers outdoors, but your pixels need to be very large. And so this is the resolution you get. Not only you don't see the object, but you have really hard time to see the dots. And so you don't know the depth information. In comparison, we can do easily 13 megapixel sensors in a third of an inch image format, which can give you not only the objects, but also all the dots at 940. Global shutter, why is it important for outdoors applications? This is your signal level of the sun, and you have to overcome that with your LED or VXL illuminator. So if you have a DC or rolling shutter sensor, you have to have your VXL or LED on all the time and to a level where it's over the sun. Not only is it dangerous for your eyes, but it's only a lot of power in your camera. Therefore, you want to pulse it. So you duty cycle it, you pulse it very short, but very high in peak. And to do that, you need to take a snapshot with all your pixels at the same time. That's why the global shutter is a must-have. And right now, for small pixels, like micron pixel sizes, quantum film sensors are the only one that can enable you with the global shutter. This is an outdoors image. What it looks like again, a comparison with the CMOS camera. This is a CMOS camera at 850 nanometers. There is a projector. You might see some dots here, but there are definitely no dots here or in the background. And the reason is at 850 you have a lot of light from the sun, and silicon quantum efficiency is not very high, so not a great picture. You're not going to get any 3D or depth information from it. On the other hand, quantum dots enables you to go to very smaller, much smaller pixels with global shutter. You can see all the patterns of a curtain here and the pattern of your drone. So to conclude, we started with a solution of quantum dots, which is really like a fluid that you can spin coat on your wafers very easily. You take your standard wafer, anyone can do it. We offer services, actually. If anyone is interested in having your sensors have quantum dots, we can do that, as long as you give us wafers with the top metal exposed. And the wafer coming back from us will look like this, where the dark is the quantum film. And then you dice it, you can build camera modules. This is maybe a more familiar image of what you get in a cell phone. And then you can integrate on laptops, drones, DSLR, and cell phones. And these are two pictures to show the technology that we have today. These are taken with our 13 megapixel sensors. This is a picture taken with a visible sensor. So it's a 13 megapixel, 1.1 micron. We put visible quantum dot solution, so there is no infrared information. And we put RGB color filters, and then the post-processing, you can extract the colors, and you get these very nice, pretty images where the colors are really well represented, and the dynamic range is very good. This is a picture taken with our Spark line. The Spark line is image sensors with near-infrared quantum dots, which means they are tuned to see in the 850, 950 nanometer. So there is no color information, there is no color filters, no micro lenses, and you get an image which looks a lot different from the color one. But this is for humans, this is for computer vision. All right, thank you.
Questions for the speaker? It's a little hard to see out there. Okay, I have a question. So you mentioned the quantum dots. But what are they? What are quantum dots? Where do I buy them? Can I? And what are they made out of?
It's actually confidential information, how we make the quantum dots and the materials we use. But there are a lot of publications of quantum dots, cadmium, and we don't use any hazardous materials, so they are okay with for commercial products. But they are basically nanostructures, nanomaterials, which create quantum confinement wells, and therefore it's an equivalent of a band gap. So it's not an organic material, but it's a crystalline nanostructure.
Great. Okay. Let's start with a question on the over here.
Hi. Could you speak a little bit to the medical applications to full spectrum rendering, please?
Yeah, that's a very interesting market and application, I would say. We are looking at medical imaging as well. We have tried both infrared and UV. We are trying to push the boundaries on both ends of the spectrum. where we cannot go right now all the way to X-rays or on one end, or gamma rays or photo emission on the other way for like PET applications. But whatever is in the range between 350 and a micron and a half, we can do.
Thank you.
Mm-hmm.
On the right.
Bob Stewart Research Enterprises. I was wondering, continuing in the range of questions the session chair was asking you, what's the band gap like? What's the Fermi level like? Can you discuss the model you use in terms of treating quantum dots? Is it a photon-based rather than a wave?
So I'm not sure I got all the question, but you were asking how do we use the quantum dots to convert photons in electrons? Is that the question?
Why the advantage over silicon? It must relate to things like the...
Right. So the short answer is silicon. You have one band gap, and you're tied to that. You cannot move it. Quantum dots, the equivalent concept of band gap is adjustable. So you change the size of the dots, that ring that is the quantum dot, and you can change the band gap. 0.7 volt, 0.8, 0.9, 1 volt, or going lower, 0.5, 0.4. So it's like having a material that you can adjust the band gap off depending on your needs. That's the big advantage.
So the size of the quantum well
Yep.
changes the solution to the Schrödinger equation, so you do get a
correct
variable
yes.
band structure.
Yep. Yep. Correct.
Hi, great presentation, Dr. Emanuele. I'm Rakesh from Oracle. My question is, you made it look very simple. Can you touch upon some of the challenges that you ran into during this, and adoption challenges, and talk about cost?
Sure. Yeah, it's not very easy. Invisage is a 10 years old startup. So for a startup is a long time, but it's a testimony of how hard it is to get to this point. It started with just the dots in a solution, and the founder, Ted Surgeon, he had the idea of absorbing light with it because he noticed that. And from that to build reliable quantum dots in volume and spin coat them on wafers, controlling the thickness accurately, capping them with the materials to create not only an electrical top contact, which has to be transparent, like an ITO, ACO, but also have the right thickness to act as an anti-reflecting, and go through reliability and manufacturing. Takes a long time and a lot of money. So that's why we are at the point where, yes, we can come out and talk about it because we solved all the technology problems in this 10-year span. But yeah, if someone wants to produce image sensors with quantum dots tomorrow, I think it's going to be a hard way.
I had one last question. So, one of the very interesting applications you showed was essentially using structured light in an outdoor scenario. Yep. So I was wondering, kind of looking more broadly, if we have a lot of devices that are making use of structured light, then now we have to agree on like what colors different devices are supposed to use, or like what time periods they're supposed to use it, so that they can all like get that information. Mm-hmm. So where do you see that problem being solved? Is that solved at the sensor level or at some other level?
Yeah, very interesting question. Like, for instance, autonomous cars, right? If you look at the cars you have around today, like the Google cars, they have this hump on the top. That's a LiDAR. So it's a rotating laser which takes images. And you might think, number one, if I have a lot of cars, now all your cars are autonomous, will they interact with each other? For LiDARs, yes, that's true. There is interference. So you have to make sure that you're not illuminating the same object at the same time. For structured light, is actually the opposite. The more cars you have, the more illuminators you have, the more dots you have on the image, no matter if it's your dots or someone else's dots, but they pattern the scene. And so you receive, with your passive sensor, with your camera, the image with a lot more dots that you projected. That's actually good, because the pattern of the dots is random. And all you want to know is how close or how far the dots are. So it helps you. Having multiple illumination sources helps you.
Great. Let's thank the speaker.
Right. Thank you.
Okay, our last talk in the session is entitled Clear Motion, Building the World's First Superactive Suspension System. Our speaker is Dave Weatherwax, who's Director of Software and Controls Engineering at Levant Power. Prior to Levant, Dave held leadership positions at iRobot, where he worked on a variety of military ground robots and consumer applications. Dave received his BS in Electrical and Computer Engineering from Worcester Polytech Institute.
Thanks. Thanks for that intro. I'm really excited to be here today to talk about what Clear Motion, formerly Levant Power, we actually just changed our company name, and this is, I think, the first presentation with the new company name. I'm really excited to show off what we've been up to. So the title of this talk is Building the World's First Superactive Suspension System. So my goal today is to explain what that actually means, show off the product that we're building, and dive into its design. This talk is going to be more of an application of embedded systems versus going into detail on any particular piece of silicon. ClearMotion actually doesn't build their own custom silicon, so I hope you enjoy it. Okay, so here's what we're going to cover today. We're just going to briefly give an overview of what the product is that we're building, and then we're going to spend most of the time diving into the system architecture, looking at the mechanical, electrical, software and controls, how we integrate into a vehicle, and looking at some of the performance and tuning characteristics. So what I've found is the easiest way to explain what the system is to show it off working. So if we can flip to the video. I think it's on the desktop. Oh, there it is. That was fun to shoot. So that's our product. So GenShock is a super active ride control system. I'm going to explain what that means. Getting there. Okay. So the problem we're solving has been haunting the auto industry for literally decades. So typical suspensions are called passive systems that are mechanically tuned. So the tuning is essentially hard-coded at design time. And these mechanically tuned systems all make a trade-off between a good ride or the comfort of the vehicle versus the handling, the steering, and controllability of the vehicle. So the current state-of-the-art systems that are out there on really high-end luxury sedans are called semi-active, where the vehicle can control the damping rate at runtime, but these systems only provide a limited performance increase over the passive system since they can't push and pull on the chassis. And so this ability to actually push and pull using an actuator with a high level of controllability is what we're calling superactive. We're actually coining the term because there's nothing else out there on the market like this. And so ClearMotion is the first system that has this capability going into market. So I won't spend too much time belaboring the point, but the auto industry has literally spent billions of dollars trying to come up with a commercially viable system. So just starting with GM in the late 80s with the ball screw design, Nissan in the early 90s with their centralized hydraulics. Bose actually had a lot of viral YouTube videos about their pure electromagnetic solution, but that didn't make it get into the production. There actually is one system on the market right now, the Mercedes Magic Body Control. But just due to the design of this system, it has a very slow response time of about a quarter second from a force command. And so it just results in a user experience that isn't that much, it's not a step function over the passive system. So how did this little startup, started out of MIT in 2009, beat all these big guys? So that's what I'm going to talk about. So the answer is really in our software. So the solution we have is a hydraulic-based design. Instead of a centralized solution, we're localized at each corner of the vehicle. And so we basically have an actuator that's a hydraulic pump driven by a DC motor with some pretty sophisticated control algorithms. So basically with sensors in the wheels and body of the vehicle, we're able to read the road and react with a response time and control authority that hasn't been seen before. And with our controls, we have the ability to cancel out many of the negative effects of the mechanical design, which enables a low cost and low power solution that also has good performance. So just to show, here's just some pictures of some of our components. This is our custom pump, our motor, and our custom electronics. So this is actually a shot of our pump connected to a damper body. This is actually an older design. The picture's a little old, but you can see how we're basically sticking off the side of a traditional shock. Okay, so that's the product overview, and now we'll jump into the more technical stuff here. So I'll just give an overview of what our system architecture looks like, how we integrate into a vehicle. We'll walk through a single use case of how our system operates going over a speed bump, look at our control loop timing, look at some performance data and tunability, and also cover our software architecture. Okay, so here's the major components in our system. So what we have, as I mentioned, at each corner of the vehicle, we have, it's pretty close to a traditional shock absorber with what we call our active valve attached to it. So this has our, as I mentioned, our pump and our electronics and our software running right on here. So we have one of those at each corner. We also have an energy management solution. So our system can generate power, and so that gives us a place to store it, and it also gives us instantaneous power. This is all driven by a 48-volt bus. So on top of that, we also have sensors. So we use a bunch of different sensors, accelerometers in the body, in the wheel of the vehicle. We also use things like the steering wheel angle, brake and throttle position, things like that. On top of that, we have our centralized controller, which is responsible for things like our state machine in our system and any coordinated controls. Okay, so before we get too much into the electronics and software piece, I just want to briefly show a little bit about how the mechanicals work. So over here is a traditional shock absorber cutaway, like you can imagine a side view. So what we do in our system is this piston typically has some little holes in it, so we seal that off, and we actually port into each side of the damper and insert our pump. So we can basically be in two different kinds of modes of operation. We can be in this passive mode where the pump isn't running, and so basically with each stroke of the damper, fluid is forced through our pump and we can generate power. We can also be in this active mode where we're driving the pump in either direction, which will force the piston. Okay. So just switching gears a little bit, let's take a look at how we integrate into the vehicle. So over here on the right is our GenShock system. So here's our pump, motor, and controller that I was talking about. So we're powered via 48-volt bus from the vehicle. And then we have private communications with our central controller via CAN. And this central controller acts as a gateway for all communications with the vehicle. We also have some raw sensor data that we get directly from the chassis as well. Okay, so now if we zoom into this, we call it our corner controller board. We can take a look at what those electronics look like. So overall, the electronics are fairly minimalistic. There's not anything special here. We're extremely real estate bound, so a lot of the design is in just packaging these components into a tight as space as possible inside our pump housing. Our software is just running on a pretty typical automotive grade microcontroller. This is a safety critical system, so we need to be careful that we account for things like redundancy with using lockstep cores and things like that. On top of that, we have a bunch of different sensors, so encoder, accelerometer, temperature, voltage sensors, and then our motor driver circuit. Okay, so now let's take a look at a use case just to understand how this concept of active control versus regen enables this new operating mode. Okay, so what we have here is an example of a speed bump. So on the bottom right, this is a really important plot in the suspension world. So it's on the x-axis is the velocity of the shock, and the y-axis is the damping force created. So a typical suspension can only operate in these green areas, and only systems that have an actuator can really operate in the red. So if we just go through each step, at the beginning, if we're running along a flat road, so we're here at the origin, there's not really any velocity or force being generated. When we start to go up a speed bump, what we are able to do that no system can is we actually pull up, resisting against the spring to keep the body level. So this is using active energy. When we get to step 3 at the top of the bump, we're using like our maximum force to hold the wheel up against the spring to keep the body level. And then as we go down the bump, we actually let the spring do the work of pulling the wheel down, and we're able to capture some of that energy back. So it is worth mentioning that this system does have many limits associated with it that keep us from performing ideally. So we have things like power limits, mechanical stroke limits, force limits due to the motor design. So this isn't an ideal world that we're working in. So this is just one use case. Many other use cases take advantage of all the quadrants here. All right, so just to take a look at some of the control loop timing. So if we just use the speed bump as an example as we walk through this. So our system is a distributed control system. So we're doing local control loops at each corner. And then we also have the coordinated controls of our gateway. So just kind of going through the major components here. From the point of initial impact, we're sensing the body motion, body and wheel motion, using that as an input to our wheel control algorithms. It's also distributed to our central controller and used as an input to our body control algorithms. So coming out of this, so basically we have multiple control loops with kind of competing interests that we need to arbitrate and prioritize. So the output of all these control algorithms is a desired force command. And then we basically shape that force command based on things like the position of the shock, and we need to make sure we don't hit the end limits of travel. We have to be very careful about that, accounting for the inertia in the pump, things like that. So all of this decision-making happens within a millisecond. And then we give a command to the motor, which responds very quick. And then really most of the response time is getting that pump up to full force. So the overall response time of the system, and I'll show some data, is about 8 milliseconds. So also down here, we actually have this various inputs from the vehicle. As I mentioned, we have like the throttle, steering. We also have things like GPS. So we're looking at ways to incorporate a global map of road roughness to give us a chance to look ahead and know what road is coming so we can even reduce that response time even more. And then we have various tuning from the OEM. All right, so now let's look at some data. So this is a transfer function of the commanded force to the actual force. So basically, most of our work is that we're doing at ClearMotion is to try to create as an ideal actuator as possible. So a couple of these graphs are going to be on the actuator performance itself. So basically, the goal is to have a flat line at 0. So the blue line is the uncommanded system, so just the natural mechanical dynamics of the system. And then the green is our controlled response. One thing to note is 10 hertz is a real important frequency for us. That's the natural wheel hop of a vehicle. And so basically we have pretty good control up until about 30, 40 hertz. So we're pretty happy with this. And then here's our response time. So given a step input command, we're looking at about 6.5 milliseconds to where we're at our pretty close to full force. And just to compare, the only other system out there is about 1/4 of a second. So this is, order of magnitude better. Okay, so here's that force velocity curve that I showed before on the speed bump example. So this is just showing our area of operation that we have available to us with our actuator. So a typical passive suspension is tuned to a single line on this graph. And then these semi-active systems have the ability to switch between a couple different lines. So with our system, we actually have the ability to operate in this entire colored region here. And so these blue regions were actually capturing energy, and then the red were consuming power. So now jumping to the vehicle level, this is similar to that intro video that I showed the vehicle going over the bumps. This just shows the performance of the system in just canceling out those that roll behavior of the vehicle. So the blue line is the actual stock suspension. We actually can emulate pretty well the stock suspension with our system, and then the red line is with our system turned on. So one of the advantages of our system is that because it's almost all software content, we have a lot of different flexibility and tuning. So this is just showing an example. If you're taking a sharp turn, given the lateral acceleration on the vehicle, we have a pretty wide area where we can tune the roll response of the vehicle. And this can all be done at runtime. So just the x-axis here, you can imagine if you're taking a turn, we have the ability to hold the vehicle level up to a certain point where we limit on power, and then the vehicle experiences some roll. And then when our system isn't active, roll is generated. So basically, within this window here, we have the ability to tune this curve however we want. And that's really attractive to OEMs. Much of our work we're doing in software is canceling out the negative effects of our actuator. So it turns out because we're a hydraulic-based system, acoustic noise is one of our major concerns. So just due to the geometry of our gerotor, when we apply a constant torque to our motor, we have this torque ripple that occurs that just translates right up into the cabin of the vehicle. And so what we're doing is this is something that can be calibrated and understood and canceled out while we drive our motor. So this plot at the top is showing over time. Here is this torque ripple. This is kind of like a heat map, the power of the torque ripple we're experiencing, and then just our ability to cancel that out. Okay, now just look quickly at the software architecture. So on the corner controller running in the wheel well, this is our basic software architecture. So we're using a combination of pure C bare metal as well as MATLAB Simulink for our control algorithms. So we're using the embedded coder. It allows us to develop really quickly, and it's also preferred by the automotive industry as an easy way to validate your algorithms. So at the base layer, we have our own homegrown OS, sensor drivers, and then we have this hierarchy of control algorithms where we basically build up layers of abstraction from a motor to our actuator to the wheel to the full body. And each one of these loops is running at a different rate. So our motor control provides a torque abstraction layer to the system. The actuator control provides a force abstraction layer to the system, and then the higher level algorithms operate on top of that. And then as far as various protocols, we found that we're just using all industry standard, which just makes it really easy to interoperate with the different OEMs. And it turns out pretty much all the OEMs are using the same protocols and communication stacks. And then in our central controller, pretty similar to the corners, but this is where we have our body control algorithms. The overall state machine for bringing the system up and down. The central controller handles things like software update, processing the raw sensor data from the vehicle, and our API with the vehicle. So that, I think, was what I was going to cover today. I know it's lunchtime.
We have time for some questions up front. Question? On the left here.
Chris Rowan of Cadence. You talk at a number of points about power. Can you give a rough scale of the gross power that's required in one of these operations, either in or out, not net, but how much power are we talking about, and why do you need a power energy recovery system in order to be effective?
Yep. So I probably should have added a couple slides on the power consumption. Good call. So it really depends on the road that you're traveling on. So based on the terrain type, so it's based on the terrain you're traveling on and the performance that you want to get out of the system, right? So we're looking at driving a single one of our motors, instantaneous, about 90 amps, running at 48 volts is like our instantaneous, and then that's power consumption. And so depending on the terrain, it's hundreds of watts regen or active at any given time.
Hi, Shahid. I have a short question. When you were developing the active shocks, why didn't you just use an electromagnet instead of going the hydraulic system? Or what are the benefits in having it a pure electric system without the oil and the pump in it?
Yep. So the pure electromagnetic solution was actually the Bose solution that there's a lot of videos out there, but it turns out that's just too costly. It turns out having the combination of hydraulics and electromagnetics together is kind of the best cost trade-off there.
Hey, Kevin Creel, Tirias Research. Really interesting presentation. I assume also you can use it for brake dive compensation?
Yes, exactly.
And then I was going to follow up. You didn't talk about the business model. Are you looking at this as a manufacturer, an ODM solution, or an aftermarket solution?
Yep. So for the first question, the role was kind of only one use case that I talked about, but there's many, like dozens of different use cases. So brake dive is one, and there's also squat on acceleration that we have full control. So pitch and roll we have full control over in the vehicle. And so when you're in a Model S and slam on the gas to not feel the squat is pretty cool. So that's for that question. And then on the business model, our model is to be a tier 2 supplier to OEMs. So we're basically supplying to a tier 1 damper supplier who is well established and trusted by the OEMs, and they sell the integrated solution to the OEM. And we're looking to launch in 2018.
And then there's no way to aftermarket this? Like, it looked like a fairly integrated solution.
Currently, we're not looking at aftermarket solutions.
Okay, thanks.
Ron Nicholson, unaffiliated. You talked about this being an integrated solution and an 8-millisecond latency. If you're going to integrate, can you integrate in with the vehicle 3D depth sensing to sort of anticipate the speed bumps and remove the latency completely?
Yep, definitely. So the first version of the product is purely reactive, but we definitely know that version 2 of the product will be taking advantage of some of the look-ahead systems. There's systems, so all of these high-end sedans have forward-facing cameras that we can take advantage of. But the current product doesn't have that yet.
Thank you. So I'm Matthias from Hawaii. My question was pretty much the same line. Why don't you take computer vision as an input and just focus on
Yep. There's actually systems out there that generate, so a system from a company called Mobileye that does things like turn prediction, road roughness prediction. But right now we're just focusing on, it turns out, given our response time, the performance is works pretty well without the look ahead. But that's, so forward-facing sensing as well as integrating with map data is something that we're looking at right now. It's still in the more research phase. This is the first product.
Nathan Brookwood, Insight 64. There have to be a ton of safety issues associated with this in the way that it would change vehicle handling and failure modes and so forth. Are there any standards that you're governed by in terms of those safety standards?
Yeah, yes.
And how do your customers deal with this?
Yep. So safety is it's one of the top things that the OEMs are concerned about. So there's a ISO standard called ISO 26262, which handles safety critical applications. And so basically, we work with the OEM to define what the safety case is, and then we're given a rating, a safety rating. And given that rating, that dictates design parameters.
So as you go forward with this, are those concerns mostly allayed in terms of your customers, or is that still like a big...
I think I forgot to mention, one of the big advantages of our system is that we fail safe. So even if our system doesn't have any power applied to it, we have passive damping associated with it. So that's one of the biggest safety concerns. We do have some concerns about, from that coordinated controller that has control over all four wheels, what happens with it if something goes wrong. But basically, we define all those use cases with the OEM, and then we have to prove that we're mitigating them.
So we don't have a situation where Hal decides he's going to destroy the driver by vibration.
Right.
Okay, thanks.
Yep.
All right, one last question here.
Thanks. Barry Pengerly, Semiconductor Engineering. So from what I could see, it looked like you don't use a traditional spring system with this. Is that true?
We do.
Oh, you do?
Yep.
Okay. All right.
So we can integrate with either a traditional spring or an air spring, which is on some of these vehicles.
Great. Before we thank the speaker, I've been told that lunch will last until 1:20 as opposed to 1:15, so just an update. Let's thank the speaker. Thank you.